Hi all, here's a brief tutorial to help you with the phylogenetics part of Lab 4, Oral Allergy Syndrome. These parts of the lab ask you to do a phylogenetic analysis of some plants that we commonly eat. In a phylogenetic analysis, genetically based material from a variety of organisms is collected and compared to one another. The more similar the materials from two organisms are, the more closely related we conclude those organisms are to one another. Two organisms that exhibit a lot of differences are presumed to be more distantly related. If we compare every organism with every other organism, we can come up with a branching diagram called a phylogenetic tree. Phylogenetic trees are similar to family trees. Here's my family tree. I'm in the lower right corner. I have an older brother named Scott. Our mom is named Amy. I also have a cousin named Deanna. Deanna is the daughter of Lori, my aunt and my mom's sister. My aunt Lori and my mom had the same mom, Kimmy. That means me, my brother, and our cousin Deanna all have Kimmy as our common ancestor. I also have a relative named Faye, who I met while we were in college together. Faye is the daughter of Raymond, who is the son of Nowell. Nowell is Grandma Kimmy's younger brother. That makes Raymond my mom's cousin and my first cousin once removed, and all that makes Faye my second cousin. And all of us have great-grandpa Araki as our most recent common ancestor. We can simplify this family tree by taking everyone's names off except the current generation. That would look like this. Then we can connect the broken lines to simplify the picture even more. That produces a picture that looks like this. Here, the lengths of the horizontal lines represent the numbers of steps back to a common ancestor. It also represents the amount of genetic divergence or difference between pairs of individuals. I share a lot of genetic similarity with my brother. I'm still pretty genetically similar to my cousin Deanna, but we have some differences. And I have more genetic differences with my second cousin Faye than with Deanna or Scott. Suppose I didn't know who was related to whom, for example, if I was adopted. But I had some suspicion that I was related to Scott, Deanna, and Faye. If I had each of us get our DNA sequenced using something like 23andMe, then we could match up our DNA sequences and see where we differ. The more differences, the more distantly related. So we could use that genetic information to put together this picture even if we didn't know who our parents or grandparents were. This picture is built on the same logic as the phylogenetic tree that you'll generate in Part 5 of this week's lab. Here, the most recent plants, the ones alive today, are named on the right. The lengths of the horizontal lines represent the time and amount of genetic change since the most recent common ancestor. The bar on the bottom of the picture that says 0.2 is a scale for genetic change. If we're studying genetic changes in DNA, this would be 0.2 changes per DNA nucleotide site. In our lab, we're looking at amino acid changes to proteins, so this would be 0.2 changes per amino acid site. For example, to estimate the amount of change that carrots and celeries have undergone, we can see how many of the scale bars fit. Here's one scale bar. Now we add another scale bar, and we find that a little more than half that scale bar fits. So the amount that carrots have changed from celery is 0.2 plus about 0.12 equals about 0.32 changes per amino acid site. If we want to know the amount of change since carrots diverged from kiwi, we would need to add at least one more scale bar. And then, even a little more. So the amount of change between carrot and kiwi is a little more than 0.6 changes per amino acid site. Carrots diverged further back in time from kiwi than carrots diverged from celery. How confident are we about each of these branch points? Well, that's what the red numbers represent. Those red numbers can range from 0 to 1.0. Numbers closer to 0 mean we're not very confident about the way our branches group the organisms. Numbers close to 1.0 mean that we're pretty confident about that branch point. You can see that the data make us really confident about the carrot and celery grouping, and not as confident about the apricot birch group. But given the data we had, this phylogenetic tree is our best guess. If we had more data, more amino acids from this BET-V1 protein, or information from more proteins, we could build phylogenetic trees with more and more confidence. You can think of carrots and celeries as being kind of like sibling species, like my brother and I are sibling people. Just like you would expect me to be more similar to my brother than I am to my cousin or my second cousin, you can expect carrots to be more similar to celery than to plants with whom they have more distant ancestors, like soybeans, or even more distant common ancestors like apricots. Given this, you might expect that someone who has had a bad reaction to carrots would be more likely to also have bad reaction to celery than to soybeans or apricots, at least as a first guess. Phylogenetic analysis can help make predictions about allergenic foods as in our lab investigation. Phylogenetic analyses are also used in many other ways. For example, researchers use phylogenetics to understand how infectious diseases, like COVID-19, change as they spread through the human population. It could be a pretty powerful way of piecing together relationships without using a time machine to go back in time. Thanks.